So much. Thanks to everyone for the attention. I'm really excited to share what we've been up to for the last 2 years, actually, in the Typelevel organization, and particularly around our work on Cats Effect 3. Before I get into the future or maybe the present, I thought it would be maybe interesting or illustrative to look at sort of how we got here. And so I chose the past 9 years as a place that we can kind of go through. And the starting point of this 9-year period I wanted to call out really was a paper from Runar Bjarnason back in 2012 called Stackless Scala with free monads. This paper, Runar published and then presented at Scala Days. I believe it was the one in San Jose. And really was about using the free monad pattern to restore stack safety to interpreted programs. And while maybe it wasn't necessarily about effect systems, I do think it was a pivotal point in the history of functional Scala in that it really became or really popularized the notion of free monads. Probably for about a 6-year period or so, a 5 or 6 year period, where folks were writing business applications in terms of algebras of primitives and effect interpreters. And so, really I'd say, while we certainly had interest in effect systems prior to this point, this was sort of the starting point for me as I look back at the last 9 years of when effect systems really started to take off. In 2013, we had some foundational libraries start their development. So in particular, HTTP4S, the type-level web framework, and Doobie, the type-level JDBC library, both started in 2013. At the time, both built on top of Scala Z. And something that kind of snuck in a sense, in early 2013, and sort of an unassuming pull request, was the notion of the Scala Z task effect type. So Paul Chiasano opened this PR, and it was sort of like, hey, I've been working on this thing. There's this stream library idea I'm kicking around, and I need this effect type. I need this ability to reason about asynchronous execution. At the time, Scala Z had an IO type, but it was very limited in capabilities. It was really, if you currently use Cats Effect, it was sort of like sync IO in the sense that it was just synchronous execution. And so this Scala Z task effect type appeared almost as like an implementation detail of Scala Z stream, the initial sketch of Scala Z stream. All right, moving forward a little bit, in 2014, Alexandru Nedelcu started development on Monix. And at least at this point in time, throughout 2014, Monix was really focused on interoperability with reactive streams and really the observable effect type, right? Also in 2014, Runar and Paul published the Red Book, Functional Programming in Scala. And again, I would classify this publication as another sort of turning point in functional Scala. It really helped, spread the knowledge. It really helped functional Scala really become a lot more mainstream. And in that book, Runar and Paul not only introduced things like functor and applicative and monad, and introduced things like property-based testing and how you might go about writing a property-based testing framework. But they also, towards the end of the book, really showed how to start writing a toy effect system and laid the groundwork for Scala Z stream. And you could really see some of the ideas that Paul was playing with back here when he introduced task and stream to the Scala Z project come out in the later chapters of this book. Scala Z stream had a number of releases around this time. It was adopted by a number of companies around this time, and real applications started to get built with it. But we had a bunch of things happen in the community. Not long afterwards, in January of 2015, the Cats project was started. And then later on in 2015, Paul and I created or started development on functional streams for Scala. Really, it was Scala Z Stream 0.9, the development of 0.9. But at the time, I knew that, or I had hoped that the future of functional Scala was really going to be based off of Cats. And yet we had so much production code, not only my own work, but all sorts of friends from the community, other companies. Everybody had all this production code built on Scala Z. So we needed some way to bridge those two gaps, bridge the past and present into what I thought was going to be the future, with Cats really being the foundational functional programming library for Scala. And so at the time, there wasn't a great interop story between the two libraries. This is before things like the shims library existed that let library authors abstract over such differences. And so as a result, FS2 really defined its own definitions for functor and applicative and monad, and supported both libraries. It had bindings for both Cats and Scala Z. Okay. Not long afterwards, though, Alex introduced the task data type to Monix. So Monix had observable and had the sort of reactive streams inspired concepts, but now it had sort of a first-class competitor to the old Scala Z task, as well as the new effect type that we had in FS2. And the effect type we had in FS2 really was the old Scala Z task, but sort of updated for the era that we were in, updated to support things like Scala.js and to support some of the differences, in 2015 as compared to 2013. So about a year later, in mid 2016, all of the work we had put into the initial version of FS2 sort of materialized, and we released FS2 0.9. And we released this interop hierarchy. To the best of my knowledge, this was the first attempt at abstracting over the differences in concurrent effect types, not just in Scala, but anywhere. And so FS2 had this util package at the time. You can see we have the big four. We had functor, applicative, monad, and traverse. But then we had these sort of ad hoc type classes: catchable, suspendable, effect, and async. This slide is from a talk I gave back in 2016, where we sort of went through all these details of how this interop worked between, how you could use FS2 with both Scala Z task, with FS2's task, with Monix's task, and so forth. And so this got us through that initial release. We released 0.9. Again, people built real stuff on it, but we knew we had a problem. And the problem was that FS2 having its own definition of the overall functional type classes was not really sustainable. It's one thing for FS2 to do it, but now as like a downstream project from FS2, let's say you're working on HTTP4S, should HTTP4S then be written in terms of the FS2 type class hierarchy? And so what we ended up doing is, a bunch of us met and we decided to start the Cats Effect project. So in 2017, we launched this project, and at least from a inspiration perspective, we took the FS2 0.9 type class hierarchy and reimagined it to be a little bit more general. That's not to say that the Cats Effect initial release was a port of our ad hoc type class hierarchy, not quite. I think Daniel Spiewak did the initial Cats Effect hierarchy, and we had learned a lot from the FS2 hierarchy, and we changed a bunch of stuff in that initial publication. Not long after work started on Cats Effect, we had the 1.0 release of Cats. You can see that was almost a 3-year maturation period from when Cats first started in 2015 until we really reached the 1.0 milestone. About a year after Cats Effect started, a little bit more than a year, we reached Cats Effect 1.0. So much more compressed, maturation period, only about a year. And there were some significant changes in that first year. FS2 had a number of releases on milestones throughout this year period, and things did change quite a bit. But late 2018, we committed to Cats Effect 1.0, the hierarchy. About a year later, we released Cats Effect 2.0. And I think the version number, the major version number, could be a little misleading here. There really wasn't much of a difference between 1.0 and 2.0. There were a couple of very minor binary compatibility changes that were important and we had to make, but they weren't, reimaginings of the hierarchy. And so instead, we had Cats Effect 3. We've been working on it for, like I said, about 2 years, about since the time we released Cats Effect 1.0. Cats Effect 3 is going to be released coincident with Scala 3. So when Scala 3 final comes out, we will have Cats Effect 3 final. And as the Scala 3 milestones have been released, Cats Effect milestones have followed pretty quickly. So right now there is a Cats Effect 3 milestone built for Scala 3 milestone 1. That's on Maven Central. And Scala 3 milestone 2 was just released last night. And as we speak, folks are busy getting the releases ready for Scala 3 milestone 2. Okay, so that sort of brings us to the present. But I wanted to say a couple other things about Cats Effect 2. Hopefully what the history shows you is that Cats Effect 2 is really about library interop, right? It was about ways in which different infrastructure libraries like Doobie and HTTP4S could write their code in a way that the preferences of the individual authors didn't force, ecosystem bifurcation, right? You didn't have like one set of libraries that were built entirely in terms of Monix, another set built entirely in terms of Cats Effect IO and so forth. So it was really about interop. That was the key message. But there was tension. Some of the things that led to tension is that there was this notion that the cats.effect.io data type was a reference implementation of the type class hierarchy. And so what does that mean to be a reference implementation? One interpretation of that is that the IO type was limited or should be limited to the bare minimum functionality needed to demonstrate compliance with the type class hierarchy laws. So for example, something innovative like tracing of IO execution should not be included in IO because tracing is not part of the type class hierarchy. So this definition of reference implementation became a point of contention. The problem is that a lot of folks were using Cats Effect IO in industrial strength code. And so folks that are using that data type, that particular effect type in their industrial strength code don't care about this notion of reference implementation. To them, the IO type is the thing that they're using and is the thing they want features added to. And one of my favorite examples of this type of conflict is this signature here, this from completable future. Completable future is a Java type, right? And we wanted some way, or folks wanted some way to bridge the gap to say, hey, if I'm working with a Java library and it gives me a completable future, give me a way to convert that to an IO. It's a trivial function to write. So everybody using Cats Effect IO could write their own version of this function. So why not PR it to the library? And when this would get suggested either in chat, or on Twitter or on, as a pull request or an issue on GitHub, inevitably there'd be a 30 message argument as to whether or not this met this threshold of minimal. Like, is this interop with a Java API really aligned with this notion of a reference implementation or not? And unfortunately, I think this is an example where this notion of reference implementation actively worked against the well-being of our ecosystem. So looking at Cats Effect 3, we want to address that type of stuff head on. And the way we do it is we have 3 artifacts, right? 3 separate jars. At the top here, we have our Cats Effect kernel. Cats Effect kernel is all about that fundamental interop for library authors. It defines our type class hierarchy and a couple of concurrency primitives. And later on in this talk, we'll take a look at what that hierarchy looks like. But that really is your core layer of interop. At the other end of our set of jars here, we have Cats Effect core. And Cats Effect core is where we define the IO data type. It's also where we define sync IO for anyone that's used sync IO. No longer is the IO data type part of our type class hierarchy. So if you've studied the Cats Effect 2 hierarchy, or if you've read some criticisms of it, there were a couple type class references, like right in the middle of the hierarchy, that would talk about IO. And so in some way, it was over-privileging the IO data type as sort of like this first class thing. That's all gone. The IO type is now in Cats Effect core. And if you don't want Cats Effect core in your class path, you don't have to put it there. And then maybe a more direct way to address some of those non-productive situations we get stuck in is we have this standard library, the Cats Effect standard project. The Cats Effect standard project depends only on kernel, so it does not depend on the IO type at all, but then defines just a wealth of data types and common utilities written in terms of the primitives provided by kernel. So I created this slide, I don't know, 2 weeks ago, a little over 2 weeks ago. I took a sampling of some of the interesting types that are in the standard library, but this area is a huge area of growth. We're seeing so many new ideas come in. Folks continue to PR new data types to the standard library. So this is by no means a complete definition of what's here. But you can see things like console integration for printing, or reading from standard in and out, a series of concurrent data structures like queues and priority queues, a series of sort of concurrency primitives, maybe primitives in quotes like semaphores and countdown latches that really are implemented in terms of the true concurrency primitives provided by the kernel. Okay, so overall, we're looking at a different set of modules, a different set of modularization, where the Cats Effect IO type now is free to be as powerful as we want it to be. And it's not tied directly into that interop layer. So let's take a look at our first Cats Effect 3 program written in terms of IO. So full set of imports here. Nothing's hidden. There's nothing, no implicits that are hidden here off the slide. We have this program that says sleep for a second and then print hello world to the console. We create that program and then we're going to evaluate it. So we call Unsafe Runsync. Note, by the way, like there's just conveniences defined now, like io.println, which could have been there before, but wasn't. And again, it was all part of that notion of minimal, all wrapped up in that notion. So anyway, program the unsafe runsync. So we go to compile this, and the first thing we get back when we go to compile this is a compilation error saying, hey, you can't call unsafe runsync. And it's saying you can't call it because there's no implicit IO runtime. And then it gives us some advice, but the advice is basically like, hey, you shouldn't really have to call unsafe methods because we've got other ways to run IO programs. But if you need to, just add this one import, right? So let's try to add that import. If we import Cats Effect unsafe implicits.global, then when we call unsafe runsync, a second passes and hello world is printed to the console. So I think what's interesting about this example is maybe not what's here on the slide, but what's not here. And in particular, if we look at that call to io.sleep, and if you've used Cats Effect 2, you'll notice we didn't need to define any implicits. We didn't need this context shift of IO or this timer of IO, both of which we would have needed in Cats Effect 2. And furthermore, we don't see it in that example, but like this whole notion of blockers are gone. If you've used Cats Effect 2, the idea behind a blocker is that it was a way to sort of have a blocking call, something that did you know, like access to the file system, access to the network, something that was going to prevent execution, right? We could do that blocking call in a way that wouldn't tie up a thread in our compute thread pool. So you can imagine like this call to b.delay here is going to shuttle off, you know, some task to a dedicated thread pool. In this case, it's probably a thread pool that is free to create new threads for execution, but keeps them around, you know, cached for so long. Evaluate this particular blocking call, and upon completion, you know, shuttle execution, the result back to whatever the compute pool is. And you know, if you can imagine the blocker implementation, then since it's dealing with like this separate pool, it must have had some type of resource initialization and finalization, right? Like to create a blocker, we're creating some thread pool. And when we're done with the blocker, we want to terminate that thread pool and make sure we release all resources back to the operating system. So like this pattern of having to pass blockers around ended up really being viral through all the APIs built on this concept, right? You'd see blockers get passed explicitly all over the place. And then in the main of a given application, you'd have to create, instantiate a blocker, as well as, you know, release it, typically through like a call to bracket or a call to, you know, Cats Effect's resource abstraction. Anyway, that's all gone. Just like getting rid of context shift and timer, in Cats Effect 3, we can make this call io.blocking and then pass our files.delete here. So it's an example of how we're optimizing for the developer experience, right? We wanted these straightforward, you know, common patterns to be as simple as possible to implement. Beyond just things like avoiding the need for implicits, for working with time, avoiding the need for blockers, there's a bunch of other new features in Cats Effect IO itself. We have tracing now. And in particular, magic stack traces, right? So like we can trace the execution of a given IO program, but we can also say anytime an exception is thrown in the evaluation of an IO, we rewrite the stack trace of that exception to show you the history of execution as it flowed through the interpreter. Right? If you've worked with Cats Effect IO in the past, you may have the experience of getting an exception and maybe having a couple lines that made sense, but eventually you hit the interpreter, you know, trampoline or the interpreter run loop, and you can't really see what happened before that. Now you can, you can see this whole history of evaluation. So here I'm looking at some FS2 exception, and all these calls here, you know, through apply and flat map and so forth, are all asynchronous evaluations through the IO program that would not have been visible before. It would have terminated like right here at the bolded line. Furthermore, Cats Effect IO supports things like auto yielding now. So this was one of the differentiating features between IO and Monix's task, is that IO never auto shifted to thread pools. It always, you always had to be very explicit about when you wanted shifting. Unfortunately, that led to fairness situations, right, where we would never shift, and you could write programs that would, you know, in essence, live lock, you know, because certain fibers would dominate usage of the compute pools. So by default, Cats Effect now yields every so many flat map calls. And then, you know, we have a bunch of additional features, things like fiber local state, the equivalent of thread locals. This is something that all of the other popular effect types had picked up over the last few years, but Cats Effect IO hadn't, partially because of that notion of being a reference implementation. All right, let's look at another very minor thing. It's a little thing, but little things add up. So here's a hello world program written without needing to call unsafe runsync. So here we have object hello world. It extends ioapp.simple and has a run operation that returns an IO of unit. If you've used Cats Effect 2, you may be more familiar with this syntax, you know, sort of the Unix style syntax, where the run operation is given a list of string arguments to your program, and you have to return an IO of exit code. if you are like me, you can never remember whether this as call should be exitcode.success, exitcode.ok, exitcode.okay. And so, and 99% of the time that I'm writing IO applications, I don't need to return a Unix, numeric exit code. So very minor little thing, right? We've got this simple trait now that if you extend IO app that's simple, you just don't have to worry about that kind of stuff. You just return, or you just write a program in IO of unit. So while this is a very simple change, a minor change, in the end, all of these little minor things add up to really provide a much better developer experience. I mentioned IO runtime is the main way in which IO values are now interpreted. IO runtime really consists of 3 thread pools. The compute thread pool, which does all of the main computation. The blocking thread pool, which is used for any of those calls to like IO.blocking. And then a scheduler for managing, things like IO.sleep and timeouts, things like that. There's a default IO runtime provided for both the JVM as well as Scala.js. And unlike Cats Effect 2, the defaults are much, much higher performing. In fact, despite all the things I'm talking about today, Daniel Spiewak predicts that the thing that people are going to like the most about Cats Effect 3 is the performance improvements they get from their programs as a result of the compute pool. In particular, the JVM compute pool that we have now is an amazing bit of work done by Vassal that really takes the ideas from the Rust Tokyo project and ports them to the JVM. And in the end, we should see major performance improvements as compared to Cats Effect 2, which was based off of fork join. Likewise, the built-in compute pool used for Scala.js is significantly better than in CE2. In particular, there are certain fairness issues with the built-in one, and we've went to great lengths to use set immediate when at all possible, but also polyfill a bunch of different tricks to make sure we get the fairness guarantees on all sorts of different Scala.js runtimes. All right. Next thing I want to do, though, is take a quick look at our type class hierarchy. So this is now looking up at the Cats Effect kernel module. Here on the right, I have the key elements of the Cats Effect 3 type class hierarchy. Up at the top in the black are type classes that come from Cats proper. And then in the blue and the red are the new type classes in Cats Effect 3. Things do change. And so since I've done these slides, we've gotten rid of this one line in the center that goes from clock up to applicative. But at least in spirit, that line still exists, if not in reality. And so it's still accurate enough that it's useful to walk through. The place I want to start is monad cancel. Monad cancel extends monad error and really provides the ability to do resource acquisition and finalization. This used to be provided by the bracket type class. And what we found is that wasn't quite the right primitive operation. Instead, this notion of cancellation and an associated notion of masked-based cancellation really was the more primitive operation. With that, we can write things like bracket as a derived operation off of these lower level concepts. So bracket, more or less, got renamed to monad cancel. And one of the interesting signatures is this uncancelable operation here. Uncancelable says, I'm going to give you back an f of a that cannot be canceled. And it's going to evaluate the f of a that you give me. However, any of the spots in this f of a that you want to allow sort of delimited cancellation to occur, places where you opt in or you cooperate with me, and you say, here's a safe place to do cancellation, we can sort of work together to figure that out via calls to this poll that you're passed. So I'm not going to give like a full in-depth example of uncancelable because it's pretty complex to go through, and we don't have too much time today. But nonetheless, this uncancelable signature really drastically simplifies the ability or everyone's ability to write leak-free concurrent code in an understandable way. I gave a talk, I think it was 3 years ago, maybe 2 years ago, where I showed how to write a concurrent queue data type and support all of these cancellation use cases. So like if you've got one fiber that's trying to dequeue from the queue and there's nothing in it, and then simultaneously someone comes in and provides a value, then that fiber unblocks and is given the value that it was asked for. We looked at those types of use cases, but then added the ability to do cancellation of any of these fibers at any point in time. And we needed to show a way in which all of those cancellations would be leak-free. So I put this talk together and I gave the talk and I thought it went really well. And afterwards, Rob Norris came to me and said, wow, that was a great talk. What it showed me is that all of the promise of functional programming is ruined as soon as we move to concurrency. Like all of the complexity I was worried about from my imperative programming days is now back because I've got to worry about all of these cancellation scenarios and all of this complexity you had to go through. And Rob was right. In the end, the model we used in Cats Effect 2 just wasn't powerful enough to make cancellation-free or cancellation-safe, leak-free algorithms reasonable. So anyway, this new model, which I believe was first proposed by Fabio Labella, based off of mask-based cooperative cancellation, really solves that to a great degree. And I would definitely look for blog posts and for talks coming over the next few months, next 6 months, that dig into the details here and really show the power of this new model. Okay, the next type class is spawn. So anything that's a monad cancel and also has the ability to start fibers asynchronously can have a spawn instance. If we can start fibers, we can also race them, like take 2 or more fibers and run them all in parallel. And the first one that completes, return, that fiber's value. All the other fibers cancel. Or sort of the dual of that, instead of racing, let's let all of the fibers that I start all complete and wait for all of them to complete, combine their results together. Those are the capabilities of the spawn type class. A little bit different than in the past. In Cats Effect 2, there was a different type class to do that. It was not spawn. The next type class is our concurrent type class. Concurrent is a type class of effects that can spawn fibers, but can also instantiate concurrency primitives. So this is new in Cats Effect 3. The ability to instantiate a ref, right? Like a mutable memory cell where you can put values atomically and get values atomically, as well as create a deferred, sort of like a promise if you haven't worked with deferreds before. The data types ref and deferred are basically the same data types we had in Cats Effect 2. What's new here is that the instantiation of them is now codified in the type class hierarchy. Right now, if you have a concurrent of F, you can use that instance to create new refs and deferred values. In Cats Effect 2, that would have required having an async type class constraint. We've got some type classes for working with time, right? So the clock type class lets us, read the system clock, either a monotonically increasing value or like a literal time value. And then we have this temporal type class, which says something that can, instantiate concurrency primitives and spawn fibers and, support resource acquisition and finalization, but can also read the system clock. If you put all those capabilities together, then you get the ability to sleep, right? You get the ability to time things out. Start a fiber and wait 2 minutes for it to finish. And if it hasn't finished, go and cancel it. That's what temporal gives you. And then finally, we have our type classes async and sync. And so notably, async and sync are all the way at the bottom. Async and sync provide the foreign function interface, provide us the mechanism to switch from the impure world to the pure world, right? We can take some non-referentially transparent expression and make it a referentially transparent value through the constructors provided by these two type classes. And in that way, they are the most powerful type classes in the library. And this was the most legitimate criticism of Cats Effect 2, is that the sync and async type classes were actually at the top of our hierarchy, not at the bottom. So if you wanted to spawn a fiber with Cats Effect 2, you would have needed in CE2 the concurrent type class. But the concurrent type class extended from async. So if you needed to spawn a fiber, you could write to the file system. You could write to the network. You could do anything in the world as a result of every type class in the hierarchy inheriting from sync and or async. Okay. Again, just like earlier, one of the interesting things here is what's not visible. Certain type classes are gone with no replacements. Effect and concurrent effect were type classes that abstracted over the ability to run effect values, run effectful programs. It was like the type class version of Unsafe Runsync. Those are gone with no replacement, with a caveat. The caveat is that if your use case for running effects fits a certain pattern, and it almost always does, then we have this new dispatcher data type. Given just an async of F, it can paper over the need to run those effect values. Again, I'm not going to get into the details here, but if you're interested, hit me up and look for a lot more about this as we get closer to release time. But in essence, things like interfacing with a Java library or a imperative Scala library that needs to invoke our effectful programs, maybe it's like interfacing with reactive streams. You can now do that with just an async of F constraint using this dispatcher type. So in FS2, we use this for our reactive streams integration, as well as some integration with like Java input-output streams. I wanted to show an example of how we might write code in terms of the Cats Effect kernel. And I thought one way we could do that is refactor this tiny little program from IO to a generic F. So here we have this operation delete. It's given a Java and IO path, and it returns us an IO of unit. And using the Cats Effect 3 stuff we've seen so far, we can implement this as io.blocking files.delete. We're using io.blocking because this is going to be some interaction with the file system, right? Maybe there's going to be a few 100 millisecond delay as a result of some disk mounting or whatever, right? So we're going to use the blocking constructor. Pretty straightforward program, no problems. Question is, how do we not write this in terms of IO and instead write this in terms of our type class hierarchy? Well, the transformation is pretty mechanical. That's the good news. So what we're going to do is we're going to define this polymorphically over a type F. We're going to change a result from being IO of unit to F of unit. And now we need some way to call blocking, but it turns out our sync type class provides us that constructor. So if we say sync of f.blocking instead of io.blocking, we get everything we need. We just need to pick up this sync bound on f. And so this is okay. This is a certainly, it's a direct port of our original program. But what's wrong with this? Can we do better? The issue here is not at the definition site, but it's rather at the use site. So think about when someone goes to call delete. If at the use site of the delete function, we're working in terms of a concrete effect type, we're working with Monix's task, then there's no problem, right? the sync instance for task is summoned from implicit scope, it's passed along, everybody's happy. But consider the case where you're working in with an abstract F. Now, in that case, to call delete, you need an implicit sync. And so really the only way for you to get an implicit sync is to make that a bound on your code, right? Like say, hey, well, my code is now going to be defined, over this generic F that has a generic sync instance. And the moment we've done that, right, the moment we've propagated this sync constraint one layer up the call hierarchy, we've defeated the entire point of Cats Effect 3, or at least the point of pushing sync to the bottom of our hierarchy, right? Because it doesn't matter that it's the bottom if generic code is all going to require a sync instance anyway. It's a complete violation of like principle of least power. And so I encourage folks to really think about it more like this. I call this this pattern like the capability trait pattern. I think I got that from Fabio. Really what we're going to do is define this trait and parameterize the trait by an abstract F. And then in the companion object for our trait, we'll provide an implicit materializer that says, if you've got a sync instance for F, I can give you a files for F. Now the body of our delete looks identical as the simple version we just wrote. So what are we doing? What's this machinery about? Why hide this sync dependency through this implicit instance of this files trait? And what I'd like to argue is that really all we're doing here is applying dependency injection, right? Is applying encapsulation of this dependency on this sync instance. And the ability here is really so that this do stuff operation can pick up a files constraint. And now when we look at this signature, we say, oh, well, do stuff interacts with the file system. It doesn't take an arbitrary sync, meaning it can do anything at all in the world, but rather takes a specific set of capabilities, the ability to call delete in this case. Okay. Yeah, you might look at this and say, hey, isn't this just tagless final? And the answer is yes, but in a large sense, I think the community overall went down a bad path by focusing on the definition of tagless final, focusing on, apologies, my dog is having trouble breathing, but it's okay. The community went down this bad path of focusing too much on the relationship between like tagless final and initial algebras and really got so hung up, I think, collectively in like this algebraic interpretation, when really this is no different than what we did in like an object-oriented approach, right? It's really just encapsulation and dependency injection. And so I would encourage folks to think of it that way. Think of these capability traits as an encapsulation of these sync requirements. Okay. Very briefly on FS2, FS2 has two main development branches right now. FS2 2.5.x is our Cats Effect 2 branch, and FS2 3.x is our Cats Effect 3 branch. Both cross-compile for Scala 3. So there are Scala 3 versions already published from both of these, and hopefully this week as the release train is moving on milestone 2, Scala 3 milestone 2, we'll see updates for both these hopefully later this week. The real theme though behind FS2 3.x is really just integration with Cats Effect 3, and then any simplifications we can pick up API-wise as a result. Things like getting rid of blockers, getting rid of timers and context shifts and so forth. It is not a reimagination of the FS2 API, right? We're not going to change the number of type parameters to stream. It's the same FS2 API that everybody's using with just some rough edges sanded off. The biggest change really is the capability traits we just talked about. The FS2 IO project in particular has interfaces to Java NIO file system work, as well as socket interfaces for UDP, TCP, TLS support for both. Those APIs when you port them to Cats Effect 3, you kind of end up in that same pattern that we just saw with the delete example, where they'd all pick up async constraints as a result of needing to interface with these underlying, impure, non-referentially transparent APIs. And if we just expose those async dependencies, then HTTP4S and Doobie would pick up async constraints. And that async constraint would propagate all the way back up. So the entire ecosystem would be still passed around async X, again, defeating the point of Cats Effect 3. So instead, we've adopted the capability trait pattern. And now you'll be able to write things like, hey, the FS2 IO project provides a files capability that has full access to the file system, provides a network capability that has full access to socket groups. I'd also be remiss to not mention the amount of internal simplifications we had in FS2 3.x. Given that it's been 2 years since the last binary breaking release, we had all sorts of internal performance improvements and just code modularization improvements queued up, waiting for the next release. The internals of FS2 3.x are so much simpler than 2.x. So feel free to take a look. With that, I'd like to wrap up and thank everybody for their time. Just key takeaways here today is that I think Cats Effect 3 takes the already class-leading concurrency support that Cats Effect 2 had. And I don't just mean Scala, but I mean functional libraries across the board, across all sorts of language communities. Cats Effect 2 takes that class-leading ability and really extends it much more. Really provides a strong foundational base for industrial strength programming. And from a project health perspective, is in a better spot than it's ever been. I have a list of an amazing set of contributors here. The Cats Effect maintainership has grown with all sorts of new contributors contributing all sorts of new stuff. And this, by the way, is by no means a full, complete list. But these are folks that have really contributed a lot over the past 2 years. So anyway, thank everybody for their time, and I'm happy to take questions and Q&A.